Let's start with notations. How do we describe a state of 2, 3, 4 n qubits in general? So let me use my simple icon. So remember, this is my qubit. I take inspiration from a two-level atom, but it could be anything else: spin up, spin down, a current in a superconductor going this way or that way. Whatever, any physical system that you can take, and you can pick up two states, you can distinguish those states, and then label them as 0 or 1, and another one as 1. So that's our one qubit, and we've been looking at one qubit, and I think you're probably bored by now, because you should know pretty much all there is to be known about the single qubit case. So welcome to a more interesting scenario. So we can start adding qubit to our system, and we take, let's add another qubit, and yet another qubit, and a few more. So let's say altogether you have n qubits in your system. Now I put this sort of a tensor product symbol, which will have its own meaning, but for now you just think about it as adding a subsystem. And mathematically speaking, your single qubit lives in a two-dimensional complex Hilbert space, and this one in the same kind of space, and this one and this one, but all together they will live in n-fold tensor product of those spaces. And we will go into the technical details later, but just for now think about the tensor product as a statement that I have one system, another one, so it's just like constructing a situation where you have many subsystems to deal with. So now this qubit could be in state called psi1, this could be in state psi2, this can be in state psi3, and say this one in some state psi n. And then you would write, if this is indeed the case, that we can attribute individual states to every single qubit in the system, we say that the total state psi is a tensor product of those individual states. Instead of writing psi1 tensor psi2 tensor psi3 tensor whatever, physicists like to drop the tensor product sign. So we'll be quite often writing this kind of state as psi1 psi2 psi n. And of course, if you look at it, those individual states can be also state 0 and 1 chosen from each single qubit. So for example, we can construct, in fact, a very convenient computational basis out of the logical states of individual qubits. So for example, we can have a state 0, so the first qubit is in state 0, say the second qubit is in state 1, and so on and so forth, and the last one, say, is also in state 1. So for the basis states of this type, for the computational basis, we even sort of simplify the notation, and we write such a state as a state 0, 1. We just drop the cats, and we just have one big cat here. So in this case, you see that I have a binary string 0, 1, ... 1. So we say that the system at this point represents a binary string called this binary string x. So x is a set of zeros and 1 of length n. And you can see that given n qubits, you can represent all possible binary strings of length n, right? So we have we can choose this qubit to be either in state 0 and 1, and this one in state 0 and 1. So altogether we have 2 to the n binary strings of that kind. So therefore the most general state of those n qubits, psi, can be written in terms of a superposition of states from this computational basis. So let me just write it as sum over x, where x are those binary strings, cx, x. Now, if you look at this expression here, you can see that here, because we have 2 to the n of those binary strings here, we have 2 to the n coefficients, c, x. So the most general state requires something like 2 to the n state, 2 to the n numbers, to complex numbers to describe the state. So we need 2 to the n amplitudes, which will tell us, what is the probability amplitude that the system is in state 0, 0, 0, 0, and then what is the probability amplitude that the system is in state 0, 0, 0, 1, and so on and so forth. That means that certainly not all states that we are going to discuss will be of this particular tensor product form. Because think about it this way. In order to describe individual state of a qubit, we need just 2 complex numbers, right? So just probability amplitude that your qubit is in state 0 and the probability amplitude that your qubit is in state 1. So when you have n qubits, you have 2 complex number for this one, 2 complex number for this one. So if you can really just write a product state, a tensor product state like this, that kind of states can be characterized by 2 times n complex numbers, like 2 complex numbers per each qubit. So you can see that there is an enormous difference, of course, between 2 times n and 2 to the n. So this is huge. Think about it this way, and the dimension of the Hilbert space, which is n-fold tensor product, is 2 to the n. So that's a huge space, right? And the states that can be written in this particular form have only 2 times n parameters. So that means that those states that we will be calling separable states, I will just give you specific examples in a moment, form a tiny, tiny, tiny fraction of the whole Hilbert space, of all states that are in that Hilbert space. So most of the states cannot be written in this form, and they are called entangled states. So we have now a tiny fraction of states of n qubits that you can write in such a way that you attribute individual states to every single qubit. So psi 1, psi 2, psi 3, all the way to psi n. In this case, how many complex numbers do you need? Well, you need 2 complex numbers per each qubit to characterize the state of each qubit separately. So altogether you have 2 times n. Well, that's not the most general state. That's a very special state, in fact, of n qubits. If you look at the whole picture, you see that n qubits, that means I can prepare, if you look at the basis states, I can prepare 2 to the n different configurations. If I look at the computational basis in particular, I can use my n qubits to represent 2 to the n binary strings. So the dimension of the Hilbert space of the tensor product, this n-fold tensor product, is 2 to the n. So in general, you will need 2 to the n complex numbers to represent the state. And those states that cannot be written in this particular form are called entangled. So welcome to a wonderful world of quantum entanglement, and let's take a look at perhaps 2 qubits and see how interesting this quantum entanglement is.